All right, we're going to continue looking at our statistics part 4, and our focus right now is going to be on our linear regression, which is really looking at the linear growth models. So we're going to look at some examples to see what we mean. Carlos has decided to become a comic book collector. His collection currently contains 8 comic books. Every month he budgets enough money to buy 3 more. Suppose that Pn represents the number or population of comic books that Carlos has after n months. So P0 would be the number of comics now at the beginning, which was the 8. P1 would represent the number after 1 month, so that would be those 8 plus 3, since every month he's going to add 3 to that, so that would be 11. So then P2, he's going to get 3 more than that one, so I'm going to say 11 plus 3, so that will be 14. P3 will be that 14 plus 3 more, which would be 17. We have P4, 17 plus 3 more, so we get 20. P5 would equal those 20 plus 3 more, and then P6, which is 23, would be 23 plus 3, which equals 26. So if we want to plot this data on the graph, we're looking at the horizontal axis will be our months, and the vertical column, or the vertical axis, will be the actual number of comic books. So we know that after 0 time, we have 8 books. So that's our start, which you might recognize that as a y-intercept. Next, we're looking after week 1, we have now 11. So at week 1, we're at 11. At week 2, we're up 3 more, so that would be at 14. At month 3, we're up at 17. 4, 3 more. At month 5, 3 more than that. Remember how we're graphing. You're looking horizontally at the number of books we have, and we're looking down at the month. So at month 5, we have, let's see, it goes 21, 22, 23, then 24. So it's right there. Continuing on, at month 6, we're at 26. And so you can see that as we're doing that, we're kind of getting this nice linear graph. And so if I kind of continue it on, you can like see what's going to happen as we continue on. So if we want to make a prediction, and again, I kind of drew that line, but each of our data points is really just a point. It is not a continuous set of data because we don't have anything between months that he's doing. It's just each month, okay? So how can you make a prediction about how many comics Carlos will have after 1 year? So after 1 year, really that's talking about 12 months from now. So looking at our line, and we can kind of see each time we were going to go up by 3, and my line wasn't as straight as I would have liked. So I can kind of show you though, if we're up at 3, and then we're up 3 more, and then 3 more. Should have more followed a little bit more closely to that. Maybe if I used a ruler, it would be better. But it's looking like at month number 12 that we are going to be over here right below the 45. So we'll be at about 44 is what it looks like if it continues that trend. So we think that he'll have 44 comics. So the pattern that we notice in those data values is that as the months move by 1, the number of comics increases, and we know it's going up by 3. So if we know how many, the number that we'll have next month, we'll know how many he has. Let's see, find the number of comic books that we will have next month if we know how much he has this month. So using this notation, P sub n, we could look at the month before and then add 3 to it. So to represent the month before, if we're talking about for the nth one, we'll look at the one right before would be n minus 1. So this is like our current month, and then this is last month's, which is what we really did when we were looking up here. So if I kind of show, we just added 3 every time to the one that was right before it. Okay, so now the formula could get really demanding if we can only use it when we know how many comic books that he had the prior month. So we need to be able to create something a little more useful that we could use to determine how many he would have, let's say 4 years from now. So that's looking at 12 times 4 months, so 48 months from now. So we need something a little bit more familiar. And so thinking about the patterns, the other thing that you should notice is that really we're multiplying by, or not multiplying, but we're adding a bunch of 3s. And if you look at P5, for example, in order to get there, we could think about what happened. That is, it started at 8, and then it added a 3, and then another 3, and then another 3, another 3, and another 3. So by the time we get to P5, we had added 5 5s to the original number 8. And so if we keep that in mind, if we want to find P48, then what we could do is know that starting value, which was 8, so this is P naught, our start, and add a whole bunch of those 3s. And so the number of 3s really matches up with what month we're on. So we're going to add 3 of those 48s. So let's double check on that. So if I was looking at P3, in order to find P3, we knew our start was 8, and it added 1, 2, 3 3s in order to get that 17. So looking at those two, and you can double check that with the other ones to see how many 3s were added to get those values. So if we want to talk about a more general formula, we could say that Pn would be equal to our first starter value, so that was like how many comics he had to begin with, and then add to that a whole bunch of 3s, and that, remember, corresponded with what month that we were on. So there's a little bit more of a general formula. So we could actually calculate this. I guess we could. 8 plus 3 times 48, well, 3 times 48 would be 144. So if we add 8 to that, it would be 152. All right, when we look to the next question, we're kind of going the opposite way. We want to know how long it will take to reach 500 comic books. So if we don't know, we can write that as like a P sub n, and we know that he had the starter amount, which was the 8, but we don't know how many 3s that are added. We just know that our goal is to make the total of comic books equal 500. So really then we can solve this equation. So I'm going to minus 8 minus 8. We're going to get 3n equals 492. And if we divide that by 3, really we're seeing how many times we added 3. That ends up that our n is going to be equal to, if we take 492, just punching that into my calculator, it will equal 164. So after 164 months, he'll have 500 comic books. So you can see down below, these are the more general forms. We're talking about something that's growing a D amount every time period. We were talking in this case months. It was growing by 3. P naught is the initial. And if we want to know the quantity after n time periods, this is the form that we are using. So recursive uses previous knowledge, like the day, the month before, how much there was, and so you just add the 3. And that's a little different from our explicit form, which you just needed to know the initial and you needed to know how much it was changing every time period. Which this might look a little bit familiar to you. Okay, maybe not with those P's and things, but you may recognize it as something similar to this, where we have our slope intercept form. So if you've taken some sort of algebra, you may have heard that before. And the way that it works is you basically have your start, which is your y-intercept, and then you use the slope, and it talks about your rise over your run, how much you're going up for every little bit that you're running over. If you think about that with our D, that growing by, it grows by D every time period. So every time you gain a month, you go up 3 comic books for our particular example. What we're really saying there is that 3 was our slope. So just wanted to remind you something you maybe have seen before. It does call it a common difference here, which again, that's the amount the population is changing each time n is increasing by 1. So that we went month 1, month 2, month 3, that sort of thing. So we're going to use that, or at least try and create a formula like that based off of some given data here. So we have gasoline consumption in the United States has been increasing steadily. Consumption data from 1992 to 2004 is shown below. So you can see all the different data values. It has a year and then how much gas is consumed. And notice that those are in billions of gallons. And as I'm saying this, thinking about gas prices being like $6 a gallon, that's a lot of money going on there. All right, so looking at that, you can kind of see that it's not a perfect line, but it does kind of look like we have this increasing thing. Might even say it has a positive slope. So we can draw that, and you could do it a lot neater and with a ruler, which I can make that a little bit better. Let's erase that for a minute and let's see if my tool's gonna work here. So if I want to draw from here all the way to there, we have that nice straight line. But if I want to actually write the equation for it, we got to see how things are changing over time. And so I mentioned the word slope, or D, but what's going to happen there is actually looking at the change in our Y, the gas consumption, over the year and how we're changing by years. So you can see that the years are counting up. We have 1992, 1993, 94, 95, 96, 97. That's where all our data points are coming from. And we can see how we're changing every year. And so when I look at that change, it's not so consistent, and that's why we don't have a perfectly straight line with our data. So the first change is by 1, the next change is by 2, the next one's by 3, and then we have a change by 2 again. But we can try and fit a curve, and the way that we're going to do that is just pick 2 data points. And so any data points, preferably the beginning and end of our data set. So if we're going to do that, let's think about that significance again about the slope. And so that slope is going to be the change in gas consumption really per year. And so if we want to write an equation in order to help us actually predict what might happen in 2024, again, I wouldn't want to use the recursive one, but the explicit one, we could say that the population we'd expect, which is really the gas consumption we'd expect, would be equal to the initial starting amount. So we're kind of looking, if you refocus on the graph, at 1992. So we can call that our like year 0. And so at year 0, it looks like about 110. And I could verify that with my data table that at year 0, I'm at 110. And then if I pick something near the end of my data set, so if I picked like 2004, we could say, okay, well, 2004, what year or what yeah, if this is our starting year, 0 was 1992, how many years to 2004? So we're like 1 year, 2 year, 3 year, 4 year, 5, 7, 8, 9, 10, 11, 12. So by the 12th year, I'm at 136. Zoom out just a little bit. And so if I want to see the change there, I can say, well, my slope is the change in gas consumption, 136 minus 110, over the change in years, which would be 12 minus 0. You could just say 12. So 136 minus 110 is going to be 26 over 12, which you could reduce that if you'd like. We say 26 divided by 12. It's going to be 2.1666666 or 2.17. If you want to leave it as a fraction, because it is that repeating decimal, we could say that our slope, 26 over 12, equals, dividing just by 2, it's 13 over 6. So we could say it's going to be that initial value again, which was 112, plus 13 over 6 n. So if we're using the year 0 here as 1992, and that's the 110, if we want to see what's going to happen in 2024, and we want to figure out what year that is, we could take the 2024 and minus off that 1992. And that would tell us how many months or how many years we're talking about. So we have 32 years. So according to our little formula, we know that P32 would be equal to that initial plus, if it had this rate of change, 13 over 6 times 32, which would be equal to about 181.33333. So I'm going to round off to about 181.3 would be what we would expect in the year 2024. So if we continue that trend, if we want to know when there will be 200 billion gallons, we can put in our P sub n equal to this 112 plus 13 over 6. Set this equal to that 200 billion and solve for that n. So if we minus 112, we get that 13 over 6n is equal to 88. We can divide by that 13 over 6, and we end up that n equals about 40.6. And so this is after, so that's the number of years after 1992. So if we're trying to find after 1992, 40.6 years from there will be equal to in 2032.6. So really by 2033 we would be at that consumption of 200 billion gallons. Now, just a little reminder that we used these two data points. I used 0 being the 110 and 12 being the 136. And if I would have chosen other values that were not those two endpoints, then our line could be slightly shifted. So your numbers might be a little bit off. If, for example, you used the 111, which would be year 1, with the 1993 with the 111, so year 1, and had 111. So like if you use that with the year 2003, that would be 10 years later, and that consumption was 133, you're going to have a slightly different answer. So just a little example, if I'm finding the slope of this, or that change, the change in my y values and the gas consumption from 133, it came from 111, that would be 22. And then the years, it's a 10-year difference, 10 minus 1. actually 9 years. And so that's going to be a little bit different of a slope, right, than what we had using those 2 points. So again, it's just an approximation to get an idea of a line, so that way we can use it to predict. So again, your numbers might not be exactly what I have here, but it should be pretty close.